This is section 6.4 on the topic of least squares solutions. And we're going to see here the basic idea of this section I've summed up to start out. Given a system AX equals Y, M equations and N unknowns. So in other words, A is an M by N matrix, M rows, so M equations, N columns, meaning N variables, unknowns. So that means X, the column of unknowns, is in Rn, since there's N of them. And Y, the other side over here, must be the same as the number of equations. Right? Those are all the right-hand sides of the equations. So that's in Rm, the number of equations. So given a system AX equals Y with this description, if it's inconsistent, right, meaning it has no solution, the idea of this section is, well, can we find a vector X in Rn that makes AX as close to Y as possible? So we are going to call that vector that makes AX as close to Y as possible. Even though it can't equal it in the case of an inconsistent system, we can find the closest thing, the closest X, so that AX, the X so that AX is as close to Y as possible. So let's give this an actual definition here. Let AX equals Y be a system of M equations and N variables as described above. A least squares solution, that's what we're defining here, a least squares solution of that system AX equals Y is an element that we're going to call X hat here, X hat, in Rn, such that Y minus AX hat in norm, so the size of that difference vector, is less than or equal to the size of Y minus AX for any other vector X in Rn. So out of all the X's you could put here, this X hat makes it as small as possible. And notice when we're taking the difference of two vectors and then taking the norm, that's really the distance between those two vectors, Y and AX hat. AX hat minus Y in norm, it's just the distance between those vectors. So all we're really saying is that exactly what we said up here. We are just finding the vector that makes AX in our system as close to Y as possible, even though we can't make it equal it in some cases. So let's break this down a little bit more. By definition, for any X in Rn, AX is in the range of A, right? When we multiply by A, we're really getting a linear combination of the columns of A. And so that is actually a vector in the range of A. Right? Remember, the range of A is the subspace spanned by its columns. This is all the outputs that A times a vector can produce. That's really the range of A. Okay, now if AX hat here, A times the least square solution, is indeed the value of X that makes AX as close to Y as possible, then we can kind of look at this picture here and get a sense of what's happening. Right? Y is this vector that is outside of the range of A, so no vector X times A will give you this Y. X times A for any X has to be in the range of A. So it's stuck in this plane as I've drawn it here, this subspace. So we're saying, okay, well, there's lots of vectors X such that AX is in this range, right? This black vector over here, this short one, that's one of them. But what I want is what I've indicated in red here, the vector AX hat, so that AX hat is the closest thing in this range of A to the Y vector we really wanted. Right? And so what should this AX hat vector really be? That should just be the projection of this Y down into the range of A. Right? The range of A doesn't contain what we want it to contain, so we see what's the closest thing in the range of Y to what we really want, to Y. Right? Well, the closest thing should just be the projection of Y down into that subspace. We've seen the closest thing to a subspace, or the, I should say given a vector outside a subspace, the closest thing in that subspace to the vector is the projection of the vector onto the subspace. So really, if we've got the right vector here in red, that AX hat, that should be the least squares solution. That should be the projection, AX hat should equal the projection of Y down into the range of A. So another way of phrasing all this is that a least squares solution to our original system is just a solution X hat of this new system ax hat equals the projection of y down into the range. So if I have an inconsistent system, I can just project my y value, my right-hand side of my system up here, project that into the range of A, and there will be some x that gives you that y when multiplied on A. So that's the idea here. We can trade out, instead of solving ax equals y, which could be inconsistent, we can solve ax hat equals the projection of y into the range, something that will always be consistent. Okay. And so that should minimize the distance between y and ax for any vector ax like this one in black. Any vector ax in that plane that I've represented range A by, any vector in there will give me a further distance, this black dotted line, than the distance between y and ax hat, this red dotted line. Right? Because that projection gives you the shortest distance between y and the subspace. So how do we find the least square solution x hat of a system? Well, one way is we could do exactly what we described. Project the y down into the column space of A, which is really just the range of A. Then solve ax equals that projection of y into the column space for x. The solution you get there is our x hat. It's the least square solution. So let's see an example here. Let's find the least square solution for the overdetermined system. That's what a description of a system that has more equations than variables. 3 equations, 2 variables in this case. Find the least square solution for the overdetermined system given here. And represented graphically over to the side. I've graphed what x minus y equals 1, x plus y equals 1, and x equals 1 all look like when they're graphed in the plane here. This vertical line here is at -1. Then you have your 2 lines here given by the first 2 equations. So if we want to find the least square solution to this system, we first write it as a matrix equation, which I've started down here by saying that A should be the coefficient matrix of the left-hand side, 1, 1, 1, -1, 1, 0, because there's no y in this equation. And then the y values, that's just the column on the right-hand side, 1, 1, -1. And as usual, the x is our column of unknowns. So that ax equals y is equivalent to this system. Okay. So then if we want the least square solution for this overdetermined system, using the method we described up here, we're just going to project y, this y vector, into the column space of A, which is really just the range of A, right? The space of all the things that A can spit out when multiplied on with a vector. Okay. So let's see how to do this. Well, I first need to, let's just write it down here. I'm going to say that my, the projection of y into the column space of A, well, remember how to do this. We really just want a basis for, really an orthogonal basis for the column space of A. In that case, we can just write down the projection very easily. The projection of y onto each of those basis vectors of the column space of A. Okay, finally got it written out there. Right, we've seen that to project onto a subspace, we really just project onto each orthogonal basis vector in some orthogonal basis for that subspace. So that's what I've got written out here. I haven't said what U1 and U2 are, or how I knew there were 2 of them, but let's look at that, 2 instead of like 3 or 4. Well, we're talking about a basis for the column space of A. And in this case, the column space of A is just the space spanned by these 2 columns. Right? Well, take a look here. You can actually check these happen to be orthogonal. because their dot product is 0. And they are certainly linearly independent, right? Because they are not a scalar multiple of each other. For two vectors alone, a set containing two vectors, linear independence just means they're not a scalar multiple of each other. So we already, just by taking the columns of A, we already have an orthogonal basis for A. This is great. We kind of get to skip some steps, making this projection of Y into the column space of A very easy in this case. So I'll erase my mess here. That's my explanation. Maybe we can just write it down clearly now. So let's say the basis, the orthogonal basis we can use is just, in this case, happens to be the set of columns here. In general, you might have to use Graham-Schmidt on those columns to get an orthogonal basis out of them. Or I'd say probably reduce out any, cast out any dependent vectors from that set of columns, then perform the Graham-Schmidt. But here we got lucky. This happens to already have columns that are orthogonal and linearly independent. Therefore, they already form a basis for the column space of A. You could use any orthogonal basis, but don't make it harder than it has to be. Here we were served one up, let's just use that. So then our projection of Y into the column space of A is really just projection formulas here, make this easy. Y dotted with U1 over U1 dotted with U1 times U1 plus Y dotted with U2 over U2 dotted with U2 times U2 vector. And this is pretty easy to compute out. Y dotted with U1, here's Y, here's U1. You can do the math there, it looks like we get 1. U1 dotted with itself, that's this guy dotted with itself, gives me 3. Again, check that. And we're multiplying this 1/3, this scalar 1/3 here that we got, by vector U1, so by 1, 1, 1. And next we need this scalar, Y dot U2, so Y up here again, dot with U2. Those happen to be orthogonal as well, so this is 0. I don't even have to compute the rest here. The 0 scalar out front zeroes all this part out. We just have this vector 1/3 of 1, 1, 1. Okay. So we're in good shape now. We found the projection of Y onto the column space. It's 1/3, 1/3, 1/3. And so now we just solve the original system, except instead of having our right-hand side 1, 1, 1, which is clearly giving us an inconsistent system, because these three lines represented never intersect in a single point, so there's no solution to this system. But now if we put 1/3, 1/3, 1/3 in here, that's a different system of equations that won't be inconsistent. We've projected the Y that we couldn't match into the range of A so that we will be able to find a match, find the X that produces it. So now solve. AX hat equals that projection we have for X hat, the least square solution. Okay, so what do we get? AX hat equals projection of Y onto column space of A is really A, our original matrix, 1, 1, 1, negative 1, 1, 0. Times this X hat vector equals the projection we found. We projected that bad right-hand side into the range to make it good, right? To make it something we can solve for here, for our X hat. And so what do we get? Let's take a look. Well, I would just unpack this into an augmented matrix and solve from here. And when I do this, I think I can do it just one step at a time here pretty quickly. Second row minus the first row will give me 0, -2, 0. Third row minus the first row gives me 0, -1, 0. Looks like you can wipe out this -1 with the -2 and turn that -2 into a 1. You can check all my steps here. I'm just going through this quickly for the sake of the video. But I believe we end up with this, which unpacks to x equals 1/3, y equals 0. There it is. That should be our x hat, y hat, right? All we're saying is if we went back up to this picture up here, the point x equals 1/3, y equals 0, the point 1/3, 0 should somehow be our least square solution. Let's say 1/3, 0, right there. Now we haven't seen exactly what that says, but it means that this is, well, let's just leave it there. That is roughly our least square solution. Out of all the points in the plane, that one minimizes the distance between ax and y. Point 1/3, 0 does it. Yeah, so think in these equations, if I plugged in x is 1/3 and y is 0, this side over here would be as close to 1, 1, -1 as possible out of all x, y points in the plane. And that's what we're seeing. So let's move on a little further and see another way we could approach this. Maybe a more thoughtful way on the conceptual side, on the abstract side, to do the same sort of thing. This next way we're going to see is called solving the normal equations for the system, for this inconsistent, possibly inconsistent system. Notice the vector ax hat minus y must be orthogonal to the range of A. So in my picture here, ax hat minus y, right, the difference between this ax hat projection of y into the range of A, that's our ax hat. The distance between ax hat and y is this vector whose length is minimized over any other x vector we could have put here instead of x hat. Right, that thing is minimal in length. And notice, since this is the vector between y and its projection into the range, then this ax hat minus y should be, in this case, pretty clearly orthogonal to the range, right? This right angle here, it's orthogonal to the range of A. So down here, that's what I'm discussing, that for this x hat solution, ax hat minus y must be orthogonal to the range of A, which really just means, since the range of A is spanned by the columns of A, it really means it must be orthogonal to each column of A. So if we think of this A matrix as consisting of columns A1 through AN, and we let this weird vector here, ax hat minus y, just be called V for convenience, then what we're really saying here, the fact that ax hat minus y must be orthogonal to each column of A, really tells us that A1 dot V must be 0, A2, the second column dotted with V, must be 0, and so on. All these columns, every one must be orthogonal to V. Well, what can we say from there? That really tells us that we could write a matrix equation trying to express this same fact. Right, we can write this in a form like this. Right? And so we'll leave that off at the end. And so what I want to see now is that if we think very carefully about what this is telling us, this dot product, this column of dot products, remember this is the same as just taking V with a multiplied on a matrix whose first row looks like this vector that needs to dot V. So I'm going to write A1 transpose. Since A1 is a column, A1 transpose will be a row vector. And A2 transpose will be the second row vector. And a little more space, all the way down to AN transpose being the last row of this matrix I'm creating. And so this dot product, this column of dot products, that's the same as taking this matrix whose rows are A1 transpose, A2 transpose, which is the transpose of A's columns, and multiplying that by vector V. Right, to do a matrix times a vector here, you're really taking the vector and thinking of kind of laying it over this first row to make that dot product A1, V1. I'm just putting the transpose here because A1's really a column. We want it to look like a row here. But then what do we have? We've got this, clean up my mess a little. We've got this left-hand side can be expressed as this matrix multiplication, this strange matrix I've got times vector V, and the right-hand side is just the zero vector with n rows. Well, what do we have here? What is this matrix? Keep in mind, I've just got in the first row of this matrix, I've got the first column of A just laying over on its side. In the second row of this matrix, I've got the second column of A just laying over on its side. This is exactly just matrix A transpose. And so at the end of the day, what are we really looking at here? We have A transpose times V equals the zero vector. That's the same as A transpose times, well, what was V? V was AX hat minus Y. So I'll replace the V with that. And we can break this down a little bit. This is A transpose AX hat minus A transpose Y equals 0. And finally, we get to what we call the normal equations that say A transpose A x hat equals A transpose Y. All we're saying is solve this system instead for this unknown vector, and that will have to be the least squares solution to the original AX equals Y system you started with that was inconsistent, potentially. Right. So in other words, right, we started out only with this assumption that this vector should be orthogonal to the range because it is the difference between y and its projection down into the range. So it must be orthogonal to the range. Starting with that assumption, we get that our x hat, our least square solution, has to satisfy these normal equations here. A transpose A times x hat equals A transpose Y. So let's look at a nice fact here, summing up what we're saying about these normal equations. If A has rank n, so your matrix has its range is equal to the number of unknowns, or the same number of columns as unknowns. If A has rank n, then the least squares solution x hat to this original system AX equals Y, not and here. Then the least squares solution x hat to this original system AX equals Y is the unique solution to these normal equations. So in other words, x equals x, let's say it this way, if x satisfies normal equations, then x hat, I'm trying to figure out the easiest way to say this. If x equals x hat satisfies the normal equations, then x hat is a solution. It's a least square solution. So when we asked up here, another way we could find these least square solutions, the way is to solve the normal equations for the original system. So I want to go back and do that for this case. Solve that original system we started with, which is inconsistent. Do it again, but now using these normal equations here. Well, what does this say to do? This is actually not going to be too hard. We have the same A matrix we started out with. There's our A matrix. That makes A transpose very easy to write down. We have our x vector is the xy we're trying to find. And our y vector is still that 1, 1, negative 1. Right. So with this setup, it becomes very easy. All we need to do is compute what A transpose A is, and compute what A transpose Y is, and solve this system that you get, solve it for x. But the system itself is inconsistent, but once you multiply by A transpose A, what's really happening here is if A has rank n, then A transpose A, remember, that has to be symmetric. And if a symmetric real matrix has rank n, we know it's going to be invertible. We saw this in the, I believe, the last section or two. Recent lectures, I shouldn't say exactly when. But we've seen that A transpose A, a symmetric matrix, if it has rank n, well, if A has rank n, then A transpose has rank n, and this matrix here will be invertible. You can solve this uniquely for x. Right, so that's where we get a unique solution to the normal equations. Without this requirement, there actually could be many solutions, many least square solutions. Be a whole subspace of them. I shouldn't say subspace, a whole set of them. Okay, so let's go on and actually do this now after all that talk about it. Well, this is going to be pretty easy. We need to compute A transpose A. So matrix multiplication here. When I do that, I get a 2 by 2 because this is 2 by 3, this is 3 by 2, this will be 2 by 2, outer dimensions. Okay. So the first row, first column looks like it gives me 3. First row, second column, I believe that gives me 0. You can check my work here. Second row, first column, also 0. Last row, last column, it looks like I get 2 actually. So that's A transpose A. That's this side of the normal equations. A transpose Y, we can compute that as well. A transpose Y. What does this give me? This was 2 by 3, 3 by 1. This will be 2 by 1. So what do we get? First entry here is going to be 1, I believe. You can check my work. Second entry will be 0. So there we have it. We have A transpose A. We have A transpose Y. Let's set up our system and solve. A transpose A times x equals 1, 0. I should probably write my x hat here because the least square solution is what we get out of this. So then I'm just solving this, but this is super easy to solve. We could unpack right here and say x, 3x equals 1 and 2y equals 0. Which of course means x is a third and y equals 0. Same solution we got before. That is our least square solution. The closest thing we can do to solving that inconsistent system is have x be a third and y equals 0. There we have it. So let's talk a little bit more about similar applications to things like this Let's talk about least squares curves. We're going to say that the curve best fitting a set of data points is called the least squares curve. The question is, what do we mean by best fitting? And so really what we're going to say here in this picture, when we say that a curve is the least squares curve, that it fits a set of data points that I've drawn with black dots here, fits it best. What we're really saying is that these little vertical distances between our points and the curve, d1 for the first point's distance vertically to the curve, d2 for the next one. What we really mean by the best fit, when we say least squares, is that the sum of the squares of these little distances is as small as possible when compared to any other curve of a specified type. Might be a specified degree polynomial, or some other type of function. But of all the functions of the specified form, the best fitting curve of that form is the one that makes the square of these distances, these vertical distances from your data to your curve, makes the sum of those squares minimal, as small as possible. Note, often we do try to find polynomials to fit the data. That's not technically required though. You can best fit lots of different types of functions to data, but polynomial fitting is really pretty common. Let's look at a big theorem that summarizes this before getting into a couple examples on curve fitting here. Let x1, y1 through xm, ym, so m of these data points, be a set of data points we're trying to model or trying to approximate with the function. Let y equals a naught plus a1x all the way up through a n minus 1 x to the n minus 1 be a polynomial of degree n minus 1, where the degree n is less than the number of data points we have. You might remember if we have the same number, we could actually, we'll see how it's related, but you might remember how many data points or what degree we need to exactly match a certain number of data points. Here we're saying, what if we have more data points than n, where the degree of our polynomial is n minus 1. So say we've got a polynomial of that degree n minus 1 that we're trying to fit to this data up here. Well, substituting this data into this polynomial equation, your x values in for the x's, your y in for the y, leads to an overdetermined system of equations. We'll see this in practice. It actually makes m linear equations. So however many data points you have, that's how many equations. That makes sense. In n variables, the number of coefficients here, right? Those coefficients in your polynomial are really what you need to solve for. The coefficients are all you're really trying to solve for. Then it turns out that system ax equals y would have the coefficient matrix given here, a column of ones, a column of all your x coordinates in your data, x1 through xm, a column of all those squared, a column of all those cubed, all the way up to a column of all those to the n minus 1 power. Right? That's like these 1x, x squared, all the way up to x to the n minus 1, just with the data points plugged in. And the y values that go with those are the y1, y2, ym. The unknowns in this system here, ax equals y, the unknowns in that x vector, those are really the coefficients. Those are the a0 through an minus 1 coefficients. So let me even make that little note here. X is all these coefficients. Okay. Now if rank A equals n, so there's a unique least squares solution, like we saw up here when we talked about the normal equations. Right? If the rank of this matrix A is n, where were we? Yeah. Here's our coefficient matrix. If the rank of that coefficient matrix is n, the least square solution x hat to this system ax equals y gives the coefficients that you're going to use in this polynomial that you're trying to fit the data with. That least square solution gives those coefficients, and we call this, right, the least squares polynomial for these data points. So what are we really saying here? Think about your picture again. Here's your black curve, your least squares curve. The black dots are the actual data points. The red dots on the curve are the coordinates, the kind of correspond to the same x value as your data, but your y value that's actually on your least squares curve is given in red here, right? So y1 prime instead of y1. At that same x value of x1, our least squares curve isn't the same as our actual data. It's close to it. The y value there I call y1 prime. Same for your second data point. y2 prime is the y coordinate on your least squares curve. Same with all the way out to the mth one of them. And so for each of these, I'm labeling in blue the distance between the actual data in black and the distance between and this actual point x1, y1 prime on the least squares curve. So I'm saying that's my D1 here. If we're thinking about this visually like we were before, really keep in mind what's going on here. We're saying that we have this y, this vector that's not in the range of A necessarily. We want to find the AX hat in the range that is closest to that y and solve that system. Right? But this D vector, that's just the vector between whatever AX in the range we choose and our y. So I'm labeling this D vector as AX minus y. Well, we know that is minimized when we take the x to be that least square solution. When we put x hat in here, we get this red vector drawn down here. Right. But notice ax minus y here in general is just the difference between these y coordinates. Right? y1 prime minus y, y2 prime minus y, and so on. So in that case, right, we can say that this norm of this vector here, this blue vector, that's our ax minus y, the norm of that is as small as possible when x is the least square solution. Which really means when we do plug in x equals x hat into that norm, the norm squared would just be the norm of this d vector, because that is exactly what we're talking about. D is exactly that difference. But from here we could see the norm of that vector. Maybe I make it a little clearer. That vector is just a difference of y values, right? Y values, output values. So this is, and we can see that more clearly over here, this is just like y1 minus y1 prime. I think I actually put the prime here. Y prime minus y1 in norm. Right? D is just the difference between y and y prime. So, what is that though? Looking here, we can see what is the difference between our y prime vector in red. Well, its coordinates are given by these y prime scalars. And in black, the original y vector up here, its coordinates or its components are given by the y1 scalars without the primes. Y1 through ym scalars without the primes. So what do we have here? This is just y1 prime minus y1 squared plus y2 prime minus y2 squared all the way out to the last data point, ym prime minus ym squared. Right? This is exactly what we described above, that since we know this is minimizing the distance between the elements in the range and y, and we've seen here that those that sum, that norm squared of that quantity that's being minimized is really just the sum of the squares of these differences in y coordinates. This really adds up to exactly what we were saying before about what quantity is really getting minimized when we take the least square solution. Right? It's this difference in these vertical distances between the data and the the least squares curve. Okay, sorry, I made my picture a little bit of a mess up here. So let's actually do an example here where we find the least squares parabola through the points 1, 4, 2, 0, 3, 3, and 4, 5. First thing I'm going to do is write out what a parabola looks like in most general terms. Looks like this. It's a quadratic function. So according to what we saw up above, all we need to do is plug our data plug our data here into this form of our parabola. We want the A0, A1, and A2 to make the parabola that comes closest to hitting both all four of these points. So using the first data point, we plug in y is 4 and x is 1. Using the second data point, we plug in y is 0 and x is 2. And so on. Plug in y is 3 and x is 3. And y is 5. And x is 4. Okay. And so we see there we get a system of equations for these a values, right? For the a0, a1, and a2 coefficients. And you can work this out. You will find that this is actually going to be inconsistent here. But what is the matrix we're actually working with? Or the matrix equation? This is what we're working with. And we're saying that in order to get the least squares parabola, we need to solve this, or come as close as possible to solving this for the least squares solution, right? That's what we want, is the least squares solution. Okay. Well, we could try to project y onto the range of these columns. That's usually a little involved. So instead, all I'm going to do is take the normal equations, the x vector, that's just my coefficients, and solve those instead. But you don't have to try to project y and do all that stuff. You're just solving a system. Well, I know this is my A matrix, so I can write down A transpose right away. A transpose is 1, 1, 1, 1, 1, 2, 3, 4, and 1, 4, 9, 16. So I need to multiply A times A's transpose on X. Let me do that really quickly. I'll do this on the side. And when I do this, I get A transpose A happens to equal 4, 10, 30, 10, 30, 100, and 30, 100, 354. I also need to compute A transpose Y, right? So what do I get when I do that? When I do this very carefully, right? A transpose times our Y vector here. What do I do when what do I get when I do that? Let's see. When I do that, I get 12, 33, 111. And so if we want to solve this system, the normal equations here, we're actually trying to solve, or I guess we'd pack up the augmented matrix, 4, 10, 30, augmented with the last column being a 12 there, 10, 30, 100, 33, 30, 100, 354, and 111. And so from here I can just reduce down as usual to try to solve. Let me do that really quickly. I'll just do this on a calculator, on a computer calculator. And when I do this, it looks like I end up with a 9 here, a negative 6.9 here, and 1.5 here. If I didn't make any mistakes, we've got our solution now. Those are our coefficients, 9, negative 6.9, and 1.5. Those are my A naught, A1, and A2. So we have our least squares parabola. A naught is 9, A1 is x, A2 is x squared. And there you have it. So these least squares curve problems end up just amounting to finding least square solutions to typically inconsistent systems. Okay, so let's go a little bit further here. I want to go through this example, find the least squares function y equals a naught plus a1x plus a2 e to the x plus a3 sine of pi fourths x for this data here, these 6 points I've laid out. Negative 2, 3, negative 1, 1, 1, negative 3, 2, 6, 4, negative 1, and 6, 2. Now, when I want to do this, it looks strange here. This isn't a polynomial, but I want to use this example to show that you can actually apply this principle even when you're not just working with polynomials. You can find the least square function of many different forms, so long as the form of your function is linear in these coefficients that you're trying to find. So for example here, if I wanted to find the coefficients at a naught through a3 that make this function most closely fit these points, well, what would I do? I would plug these in one at a time. Plug in y equals 3 and x is negative 2. There you go. You've got one equation. You might have e to the negative 2 and sine of pi halves here, but those are still just numbers here. The unknowns, you still have something that's linear in the unknowns a naught, a1, a2, a3. The next equation, I won't write all these out, just want to make sure we get the idea. The y value in the next point is 1, the x value is negative 1. So plug in x is negative 1. So that would be our next equation. And we go on and we do this for every one of these points to build a system of equations for these coefficients. And when I do this, I end up building up, really this side will be my y's, I guess. And this side is going to end up being something of the form ax, where again x is the array of unknowns. In this case, a1, a naught, I should say, through a3. But that coefficient matrix A here, you can kind of see what that's going to be, just like we could see it forming here, that coefficient matrix A coming out of these equations. You might be able to see what's going to happen here. It's going to look like this. Column of 1s, column of x, right, because that's multiplying, so we get all our x values, then e to our x values, then sine of pi fourths times our x values. We just get all these sort of function parts with our x's plugged in, and the y column over here would just be our y's on the other side of each of those equations. Let's see if I wrote that. So 3, 1, negative 3, 6, negative 1, 2. Let's see if I remembered all that correctly. Three, 1, negative 3, 6, negative 1, 2. 3, 1, just too far. 3, 1, negative 3, 6, negative 1, 2. Got this wrong. There we go. So that's actually the system we need to find the least square solution to. Right? Typically this will be inconsistent. This one you can check will be. But you can solve for the closest thing, the x that will make ax as close to y as possible. And to do that, we just solve these normal equations. Take the transpose of this big ugly matrix, that's AT, right? A transpose. Multiply that with A, then that on our unknowns equals the same A transpose multiplied with y on the other side, that's the system we're solving. So it's this guy times this guy transpose times this guy. That's our overall coefficient matrix, A transpose A. And this guy's transpose times this guy is our right-hand side, our new right-hand side that's projected. Think of it as being, well, I wouldn't say that much. Not quite projected anymore. But then we just solve those equations to get our x hat, our least square solution. And so you might see here, what we can really do is think of inverting this side, this matrix here, and multiplying from the left by it on both sides. It leaves just the identity here, which leaves the solution. And on the right side, it leaves A transpose A inverse, A transpose Y. Sometimes this quantity here, not sometimes, very frequently, this is called the pseudo-inverse. The pseudo-inverse of A. Because it's saying I can get my solution just by multiplying this big, strange matrix on the right-hand side, just like the usual consistent system can be solved by multiplying the inverse on the right-hand side. The inverse. Well, if there is no inverse, we can use this instead and get the closest thing to our solution, right? In this least square sense. So we often call that big matrix that we have to multiply the right-hand side by to get our solution, our least square solution, we call it a pseudo-inverse of A. Sometimes noted P-I-N-V of A. Okay. Now, we can only say that this inverse even exists if the rank of our coefficient matrix is equal to the number of columns it has, right? If its rank is 4 in this case. In that case, A transpose A is got rank of 4, and it's therefore invertible. Right? A transpose A is invertible in that case. And when I do this, when I take this matrix times, when I take this matrix transpose, so A transpose, times itself, invert that mess, multiply by A transpose, and then multiply all that on Y. It's a lot to do there. Make sure you got all that. Then once I do all of that, I get that my x hat, my least square solution, rounded down gives me this. Now these are just the coefficients, the A naught, Y naught, A naught, A naught, A1, A2, and A3 up here, so that this function fits this set of points as close as possible for any coefficient set. So in other words, our least squares function would be this guy. Just put all those coefficients in. And the only thing I want to do to finish up this section is to look at some numerical results here. This is what our least squares solution looks like, our least squares function. It's very strange, right? Our least squares curve. When I plot it along with those original points, this is what it looks like. Let me give it a little better view here. This is what it looks like. You can notice it's trying to stay as close to all the points as possible. Comes down in here. It looks like it somehow doesn't have the ability to hit this point and this point to bounce back and forth that quickly. So it looks like it tries to kind of split the difference between that so that it can better reach this point and very closely hit, very close to the 6 point, this 6-2 point. So that is the actual function. That's our data and our least squares curve for that very strange function, the non-polynomial fit. Let's look a little bit more at some least square polynomials of increasing degree for this same set of data. So we could look at the polynomial degree 1, the linear fit. It looks like this in green. This is our linear fit. We could look at the quadratic fit on top of that. I put that here. That's in purple here. So you notice that ability to bend means it's a little more able to try to match these points. I'd say the purple curve more closely matches than the green one. And we can up the degree of the polynomial even more. Here I've done a cubic in dark green. You see that even has more ability to bend, so even more ability to try to match the location of the points, to weave through them nicely. That's the linear, quadratic, and cubic. And finally, fourth degree polynomial in lighter blue here, again, even more ability to kind of weave through these points. It's trying to dip down here, trying to get closer to this point, reaching up here to try to hit this high point, and then coming back down and weaving again through this low and 6-2 point here. And finally, something happens when we go to degree 5, and that's in black here. And I claim this picture isn't super clear, so let me show this same thing with all the other lower order approximations knocked out of here. What if I just keep that degree 5 approximating polynomial, least squares polynomial? It hits all the points exactly. And so you might remember this from earlier in the term that if you have n distinct data points, then an n-1 degree polynomial will perfectly match all those points, can weave through all those points, can be fitted to the points. Right, so we had 6 points, degree 5 does it in this case. Look how nicely that hits all of them. The other thing I thought would be interesting to look at is our approximation through this very strange least squares function, not a polynomial. And remember, that had 4 terms in it, so sort of, I would think of it as sort of having 4 different basis vector directions. Maybe think of it sort of that way. 4 different degrees of freedom, you might think of it. And in the polynomial that has that same number of terms, the cubic polynomial, I thought it'd be interesting to look at what happens with both of those compared, something with equal number of terms to try to match the data. Well, you notice that they both do a pretty good job here, right? Kind of comparably good, in fact. It's just, I thought it'd be interesting to see if we're only allowed to take so many terms in our function, is a polynomial better than our strange function? Is our strange function better than the polynomial? I'd say it's not obvious in either case which is better, but if you wanted to test it, you could test which curve has a lesser. When you square the distances, the vertical distances from the points to each curve, and add all those up, which one is a lesser sum? You can test that on your own if you want to see which one is really a better approximation, or maybe you can look at these and sort of approximate which error might be lower. Okay, that's it for this section. Hopefully you've got a sense of how these least square solutions can be used or can be computed using normal equations or by projecting the right-hand side into the range of your matrix. But just remember these normal equations, where are they? Trying to recap of that to end. Oh, well. Okay, well, I can't find them right now. Here they are, A transpose AX equals A transpose Y. Solve that for X, and that's actually your least square solution to AX equals Y. Okay, that's it for this video.